Okay, so here's what we were doing last time. We were talking about optimization. By the way, we are going to finish today. In order to finish, we're going to have to move pretty quick. But it'll be perfectly reasonable. Also, there are some things we're going to skip. Now, the things that we're going to skip are things that are optional that I don't really need to cover. And all else being equal, I would have liked to have covered, but oh well. The time was better spent talking about other things, I suppose. Yeah.
Those optional stuff responsibility.
Now, I'll be clear as we go through. Anything that I don't talk about, I'll comment on. Yeah. So some yes and some no. Okay, so anyway, back to optimization. Remember we started off talking about interior, what we call unconstrained optimization. Unconstrained in the sense that when you're at a point like this, you can move in any direction. You could move that way or that way or that way, and you're still in the set. Right? So there's no constraints on how you move from that point. And the argument that we made in this context is, take a look at the gradient vector. If that gradient vector is non-zero, and if the function is differentiable, the function is in the process of increasing as you go that way. That can't be a maximum in any sense. It's still getting bigger. Right? So, therefore, not a max. So, here's our ruling out process. This is how we find not maxes. All right? Now, how do you find maxes is a different story. How you find maxes is sort of the opposite. It's like, anything that I can't confidently confirm is not a max, I'm going to have to call a possible, I don't know, I'm not really sure what to do with this point, possibility, right? And the name for that is critical point. So any point where this argument fails, any point where the function is not differentiable, any point where the gradient is not non-zero, aka is zero, right? Any point where either of these things happens, then our argument fails. We can't rule it out. We have to admit that we don't understand what's going on there. It might be a max. As far as we know, who knows? And we call it a critical point. Okay, so we did an example of this. And then remember, what is it actually? Again, lots of possibilities. Who knows? Right? Hard to say. All we know is the tangent plane is kind of flat there, if there even is a tangent plane. But still leaves a lot of different possibilities. Okay, we did an example last time. Here is the next example I want to go to. I just want to point to how the algebra does not always work out as conveniently as it did in that first example we saw. So, for example, let's suppose you have some function f and you take the gradient, you set it equal to 0, thus leaving you with, let's say this, for example. Maybe, right? How would you solve this? Well, there's a temptation to say, okay, so x squared minus y squared is 0, and therefore x equals y. That is extremely tempting and wildly inaccurate, right? There are two possibilities if x squared minus y squared is 0. X could be y or x could be negative y. You got to be really, really careful with this. How to see this? If x squared minus y squared is 0, then x squared is equal to y squared. And remember that when you take the square root of both sides of an equation, there is this whole plus minus worry. Okay. All right, so you have to consider these cases, and there's no sort of magically bypassing this. And you can't just, this is some complication that I don't want to deal with, and so I'm just going to ignore it. No, that's wildly inappropriate. You just can't do that. You've got to consider the cases. All right, so here we go. Let's take these one at a time. We'll start with the case where x is equal to y, which could be true. Right? And if it is, what does that allow us to conclude? Well, if x is equal to y, notice that means that you can write this algebra for y by plugging in for x as y. Right? And knowing this about y, you have these possible values of y. And of course, if y is these values, x are the same values. That gives you two critical points. Okay, so, that's how the algebra works out in that case. Right? That gives us a couple of critical points. Again, if you stop here, wildly inappropriate. You didn't consider all the possibilities. Right? This is a process of elimination, and you've got to look at all the different cases. Otherwise, you're just ignoring legitimate possible maxes. Okay. So our second possibility is that x is negative y. If x is negative y, that tells you again, plug in x equals negative y, the algebra becomes a little bit different. You're no longer replacing x with y. You're replacing x with negative y, something different. You get different results and therefore different values for y, namely 0 or 1. And if y is 0 or 1, and if x is the negative of that, then notice that x becomes those values, and therefore you get these two critical points. Okay. All right, so tempting to say 4, but of course these are the same critical point. So this point has failed to be eliminated in either case. Right? So anyway, 3 critical points, and that's how you deal with that. Is everybody on board? Okay. All right. Okay. All right, so I want to talk about the second derivative test. You all remember the second derivative test from Calc 1. And it's a classification tool if you found critical points, and how do you decide? Is this a local max or is it a local min? And the argument that was made at the time, there's different points of view you can take on the argument. People like to go to geometric points of view because it's very satisfying, and that's nice, but it's hard to generalize with geometric points of view. A nice algebraic point of view is that if you're looking at critical points, namely where f prime is 0, that means that this first order term in the Taylor polynomial disappears. And that means that the Taylor series, or let's say the second order Taylor polynomial, the dominating term in describing the behavior of the function is the second order term. So this term here, if we understand what this is doing locally, then we're good. And of course it's easy to resolve. Here we have a perfect square. That's never negative. Here we have 1/2. That is never negative, right? And so whether this is positive or negative comes down entirely to looking at the second derivative. And that's why the second derivative, a point of view on why the second derivative can allow us to classify. If that second derivative is positive, that means you're looking at something that is roughly a upward pointing parabola. And that means it's a local minimum. Right? If that second derivative is negative, that means you have a downward facing parabola. Locally, again, the dominant term describing the behavior of the function. Downward pointing, and that means you should expect to have a maximum. Okay. All right, so can we do this in the multivariable case? And the answer is yeah, we can. Here is, by the way, we're only going to do this for functions of 2 variables. There's a version of this for more variables. It's hairier, and we're not going to do that in Math 212. You're not responsible for it. Just 2 variables. And here's what the Taylor series looks like. Second order Taylor polynomial, that is. Again, what happens at a critical point where the gradient is 0? If that's 0, this whole term goes away. And again, just totally by analogy, this second order term entirely describes the local behavior of the function. So now we just have to analyze this. The way we algebraically analyzed this term was convenient. Everything was positive except for one term. Is all we needed to understand. That was a lucky break. Not so here for this term. This is weirder. Note for one thing that here we have an entire matrix that's participating in this expression. Note also we have a dot product. So this is more complicated algebra. In fact, the structure of this algebra is well beyond what we are armed to deal with in Math 212. Linear algebra is the tool that's necessary to understand this. And it's, so if you take Math 216, then we'll have all the tools we need. A lot of y'all will take Math 216. I actually wrote an exam question in Math 216 that, roughly speaking, asked students to analyze this using linear algebra tools, and I guided them through the process. But anyway, we can't do it here in this course. So what I'm going to have to do is just tell you the rule. And so this is just a blind faith plug and chug. Here is the rule. Keep in mind that this rule makes reference to this matrix called the Hessian matrix. Notice it's the matrix of all the second partials. Highly organized. Okay. Anyway, so that's something that we're going to be dealing with. Here's how it breaks down. If the determinant of that matrix is positive, then I'm going to, roughly speaking, say that this is good news, and what happens is a very familiar old story. The x second partial could be positive, in which case we have a minimum. The x second partial could be negative, in which case we have a maximum. That's the one that feels familiar. Right? Okay. That's only if that's only if the determinant is positive. That's very important. The determinant's got to be positive, otherwise that's not true. If the determinant is negative, very, very different story. In fact, it doesn't even matter anything else about any of the terms. If the determinant is negative, you've got a saddle point of some description. And now I don't know exactly which of these kinds of saddle points it is. It could be a Pringle point, it could be a shoulder point, it could be a monkey saddle. I don't know. But it's some sort of, it's not a max and it's not a min. Something weird is happening there. Okay. Third possibility, the determinant could be negative. The determinant could be 0. And just like in the old single variable second derivative test, there are some cases where the test fails. The failure of the test in this case, one of the failures, if that determinant is 0, then roughly speaking what that's saying is we can't really, the second order term is just not very dominant at all, and it's not really telling the story. In fact, the third order term is going to tell the story there. So who knows? Right? So very importantly, the test fails in that case. Don't try to give an answer using the second derivative test if the determinant is 0. By the way, also notice I didn't write this down, but there's a missing case, kind of the gap in between here. What if that second partial is 0? Right? Test fails. We don't know. Let me say it better. These are the only cases that we're addressing. Colors. These are the only cases that we're addressing and making comments on what it all means. Okay. All right. Okay, so a quick example. This is very plug and chug. We've already looked at this function. We found the critical points there and there, and so let's just plug these in and see. What does the second derivative test say? Here's our matrix of second partials. That's just a matter of taking partial derivatives. Y'all can do that. Make sure that you can do that, right? And now we plug in these points. You take this point here, plug that in. The determinant is, let's see here. Here's the Hessian determinant. It's always that formula. But you plug in that point. That Hessian determinant is positive. Right? X is positive. That makes that determinant positive, which is good news. Then you plug in and see, okay, at this point, what is this XX second partial? That's positive, so we have a local minimum. Okay. This second point, that, plug it in, your determinant's negative, end of story, saddle point. It's just straight plugging into this rule. Okay. All right. So good news. The second derivative test is very pluggy-chuggy. Just make sure you know the rules. And, yeah. Right. Okay, so on to constrained optimization. Now let me remind you what we're dealing with here. What we commented at the very start of our discussion of optimization, that if you have a two-dimensional domain with a boundary, that this is highly non-analogous to a one-dimensional domain, like an interval. And it's the one-dimensional interval, its boundary is 2 points. It is almost effortless to just say, you know what? I don't need techniques to eliminate these 2 points down to a shorter list of possibilities. How about this? I'll just always check the 2 endpoints. Right? We don't need to get fancy with that. Okay, give me a second. So, on the other hand, in this situation here, I can't just say, oh, the boundary? Oh, okay, whatever. I'll just always check all of those points on the boundary. I can't because there are infinitely many of them. And I don't have that kind of time where I could just plug in. Yeah.
How would we be able to check like the point that is not differentiable?
So the check that comes afterwards, you're talking about in the single variable case?
No, I'm talking about like using the H formula that you just get. That like we all.
Oh, that's another condition on the second derivative test. The function has to be twice differentiable in order for the Hessian to even exist. Yeah.
So what do we do if like the point is not differentiable?
Then there is no second. The test fails.
Okay.
Yeah, the test fails sometimes, right? And that's familiar from single variable calculus. The test fails sometimes. Yeah. Okay, so we're going to have to, unlike single variable calculus, we're going to have to figure out techniques for how to deal with boundaries, such as this one, or this one, right? So here the sphere is a boundary. Infinitely many points, and we can't just check all of them. Okay, so first we've got to get an algebraic hand on this. Here is a little bit of terminology. Notice that in this case, the cases that we're going to consider here, that boundary is described by an equation. That is called the constraint equation. By the way, quick observation. Not everything described by an equation is necessarily a boundary. In fact, there are plenty of non-boundaries that are described by equations. And our technique that we're going to do here is going to apply anytime your set is described by an equation that we'll call the constraint equation. So in fact, we're not going to be just considering just boundaries here. We're considering a larger category of cases of anytime your domain is the solution set to an equation. So it's even stronger. Okay. Notice all equations can be thought of as level sets. Right? This is a level set of x squared plus y squared. It's a level set of that certain function. That function is called the constraint function. Okay. So make sure to distinguish between the constraint equation and the constraint function. The connection is by way of level sets. If your constraint equation is like x squared plus y squared equals x, you've got to take that x and you've got to move it over to the other side, thus writing it as algebra equals constant, right? Before you can say, and that's a level set, and therefore this thing is a constraint function. The most important thing that we're going to be dealing with in using this technique is that function, the constraint function. So you've got to make sure, in order for this to be a level set, which is key, I almost said critical, that would have been a terrible pun. It is critical, is key that this is constant. Okay. All right. Alrighty. So here's an example of the kind of problem that we're going to be dealing with. Suppose I want to maximize a function that looks like this. And there's a temptation to say, you can't maximize that function. It can get arbitrarily big. Just let x be 1 billion. Right? There is no maximum. Yes, but if you constrain yourself to saying, I'm only going to look at points on the sphere, just points on the sphere, you can't let x equal 1 billion anymore. So you don't really have a sort of a point of view that makes it clear that there is no answer. There may be an answer. There may be a maximum value of this function subject to this constraint. Okay. So the question is, how do we find points that achieve that maximum if it exists? Quick comment. Do make a point of distinguishing between the two different functions in play here. There is the function that you're trying to maximize. This is sometimes called the objective function. That's one function. On the other hand, don't confuse that with this function. That's your constraint function. The function that describes your constraint, completely different function than the function that you're trying to maximize. And it is so easy to kind of inadvertently conflate those or, something like that. So anyway, be very careful with that. Okay, how the technique works, it's a kind of a geometry argument. First observation to make is, okay, well, we're looking at a constraint set. Constraint sets are always level sets, right, as we observed a minute ago. Level sets are always perpendicular to the corresponding gradients, right? So neat fact, this vector that we call the constraint gradient, the gradient of the constraint function, that is always perpendicular to our constraint set. So anyway, a quick observation. Why that's useful, we'll talk about in a minute. Okay, now let's think about the gradient of our objective function. So gradient of f. By the way, here's my constraint set. So I'm confined to this surface in this case. What can I conclude if my objective gradient is like that? I mean, what does that do for me? Keep in mind, by the way, my constraint gradient is always perpendicular. That's always a right angle. So just hypothetically, what if my constraint gradient, what if my objective gradient looks like this purple gradient F there? And think back to optimization that we did earlier. The idea is, look, if you've got a non-zero gradient vector, just go in the direction of the gradient. As you move in the direction of the gradient, the function is increasing. How could this possibly be a maximum? It can't be. It's still increasing. Right? That was our previous argument. Can we do that here? And no, not quite. Right? We can't just go in the direction of the gradient, the objective gradient, because that's not going to keep us on our surface. So our previous strategy doesn't work. I can't say, well, look, as you go in that direction, the function's increasing, so who cares? I'm not allowed to go in that direction. What you can do, though, is you can drop a perpendicular and go in the direction of what you might call the shadow, so in the direction of the projection of the objective gradient. Take gradient of f and kind of, go as much as you can in that direction, but while still staying in the surface. And how is the function changing if you do that? Well, if you move in that direction, the dot product with the gradient, this dot product here, is going to depend on the cosine of that angle. That angle, as I have it drawn anyway, that angle is clearly an acute angle. This dot product's positive, and therefore the function is increasing. That couldn't possibly be a maximum because it's still going up. Everybody see the point there? So yeah, I mean, we recover. I mean, we were disappointed that, okay, you can't go in the direction of the gradient, and so that argument fails. But I can go almost in the direction of the gradient, and that's fine. And again, I've eliminated this as a possible maximum. There's no way that point there could be a maximum because, well, the function's still increasing as you move in the direction of that red vector. All right, so as always, as in our previous cases, if you, what we have found here, we've got a great test here for finding not maxes. Right? Just like in the single variable case. So how do I turn this into a test for finding maxes? Well, it's a process of elimination. I have to ask, where is this argument going to fail? What could possibly go wrong in this argument? Well, one possibility is the function might not be differentiable. If the function's not differentiable, then that formula is not even true, and our whole argument comes crashing down. Right. Here's another possibility. This gradient vector could be 0. If the gradient of f were 0, then this would equal to 0, and again, I can't eliminate this point as a possibility. Our argument comes crashing down. And here's the third possibility. This vector might not be as I have it drawn here. It might not be kind of off at some angle from gradient of g. What if it is, in fact, a multiple of the gradient of, what if it's parallel to the gradient of g? A multiple of the gradient of g. If this happens, cosine theta is 0. Yeah? In which case, again, I get 0. The function is not in the process of increasing. I can't eliminate it as a possibility. So we've got to consider any time any one of those three things happens, my simple-minded process of elimination fails, and I got to recognize that I don't know what's happening at that point. Maybe it's a max, as far as I know. I'm just going to call it a critical point, and we'll figure it out later. So now, what I don't have time to talk about is, unfortunately, because we're pressed for time today. I'm sorry, I hit the wrong button. What I don't have time to talk about is my assertion that I can take these three conditions that I just enumerated, and I can trade them instead for these three conditions. It's a bunch of little details. It's micro issues to realize that these are that this is a satisfactory replacement. But technically, they're not equivalent. But this is just as good in the sense that any possible maxes will satisfy one of these three conditions, just like the first set of three. So these are easier to work with, though, and so we're going to look for points where the function fails to be differentiable. We're going to look for the sort of the geometric sort of lining up where the gradient of f and the gradient of g point in the same direction, namely one's a multiple of the other. And then we're going to look for when the gradient of g is 0. And again, I'm aware that we were previously worried about the possibility of the gradient of f being 0, but that's actually inside of here. That would just be lambda equals 0. Okay, anyway, long story, but this is what we're going to be working with, and this is kind of the picture here that if that objective gradient and the constraint gradient are pointing in the same direction, so this is what that case here looks like, then no matter which way I go on the surface, the function's not increasing. And most of the critical points that you're going to find come from this case. Okay. All right, so let's see an example. Okay, so I want to find critical points of this function, x squared plus y squared plus z squared. With this constraint, I'm only considering points on this plane. Now, again, at a glance, let's do some sort of plausibility, testing. Could this function f be as big as I want it? Yeah, sure. Make x billion, make x a trillion, a quadrillion. Make x as big as you want. You'll just have to make y correspondingly negative or something, and you can totally satisfy that constraint equation, and you can get that function f as big as you want it to be. So there's not going to be a maximum of f. That's clear. It's just not going to happen. It's easy to show that. But a minimum of f. Yeah, that's a worry, right? It's tempting to say, well, the minimum value of f is clearly 0. But is it? On this constraint, you can't be at the origin. X, y, and z can't all be 0. That wouldn't satisfy your constraint. So it can't get, this function f cannot get all the way down to 0. How low can it go? What we want to ask, right? So we want to find then what is, in other words, geometrically, we want to find the point on this plane that's closest to the origin. Okay. All right. We have a constrained optimization problem. There's our objective gradient, there's our objective function. Here's its gradient. Here is our constraint function. That's the function which I set equal to a constant to get the constraint. That constraint function, there's its gradient. Okay. All right. Now we've got to go through the list here, or three conditions. Is there any point where the function f fails to be differentiable? Well, does this fail to be differentiable anywhere? Nope. It's polynomial. Differentiable everywhere. We don't get any critical points from considering this condition in this case. I can't emphasize enough, though, you still have to check it, right? You do have to note, f differentiable everywhere, or f not differentiable, question mark? No. Something like that, right? You have to note to the grader that you were aware that yes, this is a condition that requires checking, and you have to check it. It's really important. Again, we're looking at a process of elimination, and if you don't consider all the possibilities, you cannot just declare victory on among those that you did check. So it's logically very important. Okay, secondly, and I'm going to do this one next because it's a little bit easier. What about this, setting the constraint gradient equal to 0? Is the constraint gradient ever equal to 0? Is 6, 3, 2 ever equal to 0, 0, 0? Well, certainly not. Right? It's just 6 is never 0. So very easy to check. Very important to check. Super easy to write this down. That's worth money. This is points on the test right there. Just, be sure to do it. It's a very big deal. I mean, you have to check it. Right? You can't just declare it to be nonzero. You have to look and see. Okay. Lastly, we've got to check this condition. This is what I like to call the Lagrange condition. By the way, this method is called the method of Lagrange multipliers. This factor here that we are multiplying by gradient of g, that is called the multiplier. It's just terminology. And we call it lambda because lambda is kind of like L for Lagrange. Okay, so let's look for that. Let's try to solve this equation. When is the gradient of f a multiple of the gradient of g? Well, the gradient of f, there it is. The gradient of g, there it is. And one equation at a time, one coordinate at a time, I can look at what does this say, and not hard to persuade yourself. Those are the 3 coordinates of gradient of f. These are the 3 coordinates. These are the 3 coordinates of the gradient of g, and requiring one vector to be a multiple of the other vector requires then these 3 scalar equations. Okay. Now, another point to keep in mind. Why do we write down this algebra in the first place? We write down this algebra because this is a tip-off that we need to look. This is part of our process of eliminating points on our constraint set. I only need to eliminate points that are on our constraint set. I don't need to worry about what happens at points that are not on our constraint set. We're not allowed to go to points that are not on our constraint set. I'm not responsible in any way for points that are not on our constraint set. So I am actually only interested in points that satisfy the Lagrange condition if they are actually on our constraint set. Right, so keep that in mind as well. So grand total, what you might call the Lagrange points that I'm looking for are points that satisfy all 4 of these equations. This is a real easy thing to forget. If you forget to put down your constraint equation, what you will end up with is a system that is a lot harder to solve. It's going to have a lot more solutions that most of which are not relevant. Right? So big deal, don't forget your constraint equation. Okay, and now it becomes an algebra game. It's just a matter of doing algebra. Here's a little bit of good news. You might be looking at this 4 equations, 4 unknowns. It's a little bit scary. Right? It can be terribly, terribly intractable. We're not going to give you any that are that intractable. Okay. Usually, the way to do this is to do what we call eliminating lambda. So solve for what lambda is in the 3 different equations. This lambda, for example, not hard to see. That lambda is easily 2x over 6. This lambda is 2y over 3, and this lambda is 2z over 2. Well, wait a minute. All 3 of these are all the same lambda. It is, in fact, just one variable. Those lambdas all have to be the same. Therefore, all 3 of these things have to be the same as well. And now, instead of 4 equations, I kind of have 3 equations. Right? I have, roughly speaking, these 3 equations. Okay, so that's a slick move. Having done that, it's usually just kind of a matter of plugging in at this point. So y is equal to x over 2. Plug that into there. Z is equal to x over 3. Plug that into there. Then the constraint equation becomes that. At which point you can solve for x. Once you've solved for x, you can solve for y, and you can solve for z. So the foot in the door is to eliminate lambda. The algebra doesn't always go down exactly like that. This is just a for example. If you want to see a bunch of examples of how might the algebra, Lagrange algebra work out, look at my old midterm exams. There's a bunch of examples there, and they're all a little bit different. And sometimes they have cases, and you got to deal with the cases. But anyway, it's something along those lines. Okay. By the way, so notice we did in fact only get one critical point. 632. We previously argued that, well, there's only, there's going to be a minimum. We only found one critical point. There's only one point that possibly could be the minimum. Therefore, that's the minimum. Okay. This business about two constraints. You are absolved. You have no responsibility for the two constraint case. It's at some point in the future, if you need a two constraint optimization problem done, you can look back at it. It's not that big a deal. We have the instructors have all discussed and agreed, though, that we're not going to include this in the course. So a two constraint problem will not be on the final exam. Okay. This example here is a two constraint problem. Global extreme is also not on the final exam. I want to say a couple of quick words about it, though, just because it'll help me get to the next example that I do want to talk about in the very little time I have left. And that is that when you have a set, for example, that altogether a set with an interior and a boundary, I hope this doesn't come as any surprise, but you just treat those domains separately. Look at the interior. Find critical points in the interior the way we find critical points in an interior. Look at the boundary. Find critical points on the boundary the way that we find critical points on the boundary, right? So you just apply the methods one at a time, and that gives you a complete list of critical points. So I just want to show you how that works out in this case. So here we have this set D. This is, roughly speaking, a solid ellipsoid. And if you think about it, the solid ellipsoid has an interior, right? That's the, if you will, it has an interior, and it has a boundary, like that. The interior is where you have less than, or where you have less than here. Excuse me. The boundary is where you have equals here. Okay. So I want to skip down to the boundary part. Something interesting happens on the boundary. It's easy to confirm that there's no point where the constraint gradient is 0. There's no differentiability problem. This function's never not differentiable, right? But something interesting does happen when you write down the Lagrange conditions. Here they are, and let me zoom back in for focus. So the gradient of f is equal to the lambda times the gradient of g, and you get these equations. And a lot of students will see daylight and will run for the daylight and step on the landmine. There's a very dangerous little landmine here. The daylight is, look, lambda has to be 1, but it also has to be a 4th, and it also has to be a 9th. Lambda cannot be all three of those different things, and therefore, no solutions. And that's the tempting, right? So here's the landmine. This, very importantly, does not say lambda equals 1. It just doesn't. It says either lambda equals 1 or x equals 0. You got to worry about this kind of thing. So notice this equation here. You could rewrite this as take this and move it over to the other side, and you have 2x times 1 minus lambda is equal to 0. And when you have a product equaling 0, it could be that factor is equal to 0, but the other possibility is that factor is equal to 0. Don't forget that possibility. So in this case, or in this question, we do have to again consider cases. Here, the best way an easy way to break down the cases is, let's consider what happens when x is not 0. Let's consider then separately what happens if y is not 0. Finally, what happens if z is not 0, and that's all the cases, because the only remaining possibility would be that x, y, and z are all 0, and of course, x, y, and z cannot all be 0. And notice, in each one of these cases, follow it through, and you find critical points. So it's attempting to look at this and see no critical points, but in fact, we have, from there, 6 critical points on our boundary. So just be careful, right? Heads up. Don't step on the landmines, right? Think through the delicacies of the algebra before you move too quickly. Okay, and that finishes what I wanted to talk about for the course. So we made it. Had to go a little over. Sorry about that. See y'all later. Have a good LDoc, and see you at the final exam in a week. Right.